Welcome to the eCHT research seminar. Today, for the first talk, we have Ben Spitz from Virginia. He will tell us about algebraically closed Tambara functors.
Okay, thanks. Yeah, thanks for having me here. I'm really excited to talk about this stuff. Um, right, the title of the talk is Algebraically Closed Tambara Functors. So the plan is that I'm going to tell you what does it mean to be algebraically closed? What does it mean to be a Tambara functor? What does it mean to be an algebraically closed Tambara functor? And then hopefully, what's going on with those things. Um, and I've included a nice piece of art in the title slide as a shout out to Tomer and collaborators for reasons that you'll see later. All right, but I should say this is joint work with Jason Schuchard and Noah Wisdom. And yeah, let's get going. Okay. Of course, feel free to stop me at any point if anything is confusing or if things are not confusing, but you just want to say something, that's okay too. All right, so right, I said I would tell you what does it mean to be algebraically closed, what does it mean to be a Tambara functor, and I guess I'm going to do those in the wrong order. I'm going to start with what does it mean to be a Tambara functor, and then we're going to do what does it mean to be algebraically closed. So what is a Tambara functor is part one, and the idea is that Tambara functors are some kind of generalization of commutative rings. What I mean precisely is that if you have G be a finite group, then there's some kind of notion of a G Tambara functor. For every finite group, there's a definition of what is a G Tambara functor. And if G is the trivial group, you get exactly the notion of commutative ring. If you look at the definition of Tambara functor, in the case that G is a trivial group, it reduces exactly to commutative rings. So Tambara functors are some kind of generalization of commutative rings in the equivariant direction. We have a different notion of Tambara functor for each finite group G. And when G is the trivial group, we just have the notion of commutative rings. But when G is not the trivial group, they're these slightly spookier abstract algebraic objects. But they are just abstract algebraic objects. They consist of a bunch of sets with some operations satisfying some axioms. And so I'll try to describe what those sets and axioms look like. And we'll stick with the case that G is CP for simplicity. So a CP Tambara functor, where I guess P is a prime number, CP is the cyclic group of order P, consists of two rings. So I have this ring on top called A of CP mod CP, and this ring on bottom called A of CP mod E. And I guess this would be a picture of a Tambara functor called A. So A would be the Tambara functor, and it has this top level called A of CP mod CP, and this bottom level called A of CP mod E. And these are both commutative rings. There's a commutative ring on the top, a commutative ring on the bottom. And both of these commutative rings come equipped with an action of CP. So that's the first thing. A of CP mod CP and A of CP mod E are both commutative rings coming with a CP action. But condition two is that the CP action on top is trivial. So it seems stupid for me to have actually put it there, but there is a reason. It makes the other axiom simpler. So axiom 3 has to do with these three maps that I've written down here. One of them is called transfer, one of them is called restriction, and one of them is called norm. Okay. And the first condition on these guys is that this restriction map is CP equivariant ring homomorphism. So that's where this assumption that the CP action on the top level is trivial, that just says this restriction map is going to be a ring homomorphism that lands inside the fixed points on the bottom. The action on the bottom could really be anything. Okay. And then there's a condition about the transfer map. The transfer has to also be CP equivariant, and it's not a ring homomorphism, but it will be a homomorphism of the underlying additive abelian groups. Great, so that's restriction and transfer. I have this additive map, this ring map, and this norm map is like transfer, but the other way. It's CP equivariant, and it is multiplicative. It's a homomorphism of the underlying multiplicative monoids of these commutative rings. Okay, and then there's conditions about how these maps play together. There's axioms about the map. So the first one is that if I do transfer and then restriction, it's the same as summing up all the elements in the orbit of the element I started with. I take some element down here, I have some CP action down here, so I could look at its entire orbit. And if I sum over that entire orbit downstairs, that's the same as what I would get if I just transferred up and restricted down. And likewise for restriction of norm, if I norm up and restrict down, I just get the product over all my CP conjugates. Okay, and then axiom 7 tells you how a norm of a sum behaves. And I'm not going to fill in the blank here, but there's some precise formula about what happens when you do norm of A plus B. Okay, and with those 7 axioms in place, this is exactly the data of a CP Tambara functor. That's all a CP Tambara functor is. And we're going to care about the category of CP Tambara functors. So I guess I should say, what is a morphism of Tambara functors? That's where I would have another guy. Maybe I'll move this guy over. So here's A, and maybe I have another guy, B. So here's B of CP mod CP, and here's B of CP mod E. And I've got these 3 maps. And the data of a morphism between the 2 Tambara functors would be 1 ring homomorphism on top, 1 ring homomorphism on the bottom. They both have to be CP equivariant ring homomorphisms, and they have to commute individually with each of transfer, restriction, and norm. So if I were to map over and then transfer, that would be the same as transfer and then map over. Okay, and likewise for restriction, and likewise for norm. Great. So that's the data of a CP Tambara functor. For a general G Tambara functor, if G is any finite group, the story is basically the same. The axioms become more complicated and the data becomes very slightly more complicated. Instead of just having 2 commutative rings, I'm going to have 1 commutative ring for every subgroup of G. Whatever my group G is, I take the collection of subgroups of G and I have 1 commutative ring for each subgroup of G with some actions of various groups on those rings. And always, whenever there's an inclusion of subgroups, I get these 3 maps, the restriction, the transfer, and the norm going between those various levels of the Tambara functor. Okay, but the CP case at least is like something I can write down and we can see pictures of. So I'm going to stick with drawing pictures of CP Tambara functors, but our results will work for any finite group G. Okay, cool. So that's what a CP Tambara functor is. And like, where do these come from? The place these come from is like, I don't know. My favorite place these come from is Galois theory. So let's say I have a finite Galois extension of fields. Let's say L over K. Then I have this Galois group G, the Galois group of the extension. And G acts on L is the whole point. G acts on the extension field. And we have this nice property that the fixed points are the base field K. That's the whole point of Galois theory, basically. And in this setting, when you take a abstract algebra class or whenever you learn Galois theory, you learn about these operations in Galois theory called trace and norm. And these assemble to give a Tambara functor. So if I have a CP Galois extension, then I could build a Tambara functor where at the top I have my CP fixed points, or sorry, yeah, at the top I have my CP fixed points, which is the base field. And at the bottom I have the entire field. And my group G, which in this case is CP, acts on the bottom. And I have an inclusion from the base field to the extension field, and that's my restriction. And I have a trace map, the Galois theoretic trace map up to the top. And I have a Galois theoretic norm map up to the top. Okay, and maybe you've seen these definitions before in Galois theory and maybe not. Either way is fine. But we can do the same thing, not just for Galois extensions, but really anytime I have a commutative ring with a CP action. Finite Galois extension is just a nice situation where you get a commutative ring with a CP action. So how does this work? Take any commutative ring with CP action, and we're going to define a Tambara functor. I guess S is my CP ring, and S underline is going to be my corresponding Tambara functor. And the way that's built is exactly like over here in Galois theory. I have at my top level the CP fixed points, and at my bottom level the entire thing. And there's an inclusion from the CP fixed points to the entire thing. And also there's this Galois theoretic trace and this Galois theoretic norm, and those are defined by exactly these formulas. And you can check that all the axioms work, even axiom 7, which I didn't fully write down. Okay, so that's a nice example of CP Tambara functors. Anytime you have a CP ring, you get a Tambara functor like this. But there are lots of Tambara functors that don't arise this way. And we'll probably talk about some of these later. But this does give us a nice fully faithful embedding of CP rings into CP Tambara functors. The category of commutative rings with CP action lives fully inside the category of CP Tambara functors, and the category of CP Tambara functors is actually much bigger. It's much spookier and more complicated. Okay. So, so that's at least one construction, one way to build CP Tambara functors. And it turns out this functor here, this underlined functor from CP commutative rings to CP Tambara functors, is a right adjoint. And so let's fill in that picture. There's this construction from CP rings to CP Tambara functors, and left adjoint to this is a functor that takes a CP Tambara functor and gives me a CP ring. And to do that, I could look at either of the levels of my CP Tambara functor. But the top level always has trivial action, so that's kind of boring. The interesting thing to do is to look at the bottom level of a CP Tambara functor. I take my CP Tambara functor A, and I send it to its bottom level, CP mod E. Okay. And that's always a ring with CP action. It's a commutative ring with CP action. So that gives me a functor. And this is an adjoint pair. There's an adjunction here. Okay, I won't spell out what the actual natural isomorphism is, but it's not so hard to write down. And we can go even further. If I have a CP commutative ring, I could forget down here and just get a commutative ring, just forget the CP action. And that functor that I wrote down there also has a right adjoint over here. And the way this guy goes is I take a commutative ring R and I send it to the collection of functions from CP to R. So this is just a product of P many copies of R, where CP acts by permuting the copies, is all I mean. Functions from CP to R, just arbitrary functions of sets. And then CP acts on those by acting on CP. Okay. And so this forms a commutative ring because I can multiply the elements of R, and it has a CP action because CP acts on the domain. And so that's a CP commutative ring. Nice. And it turns out that's also, that gives me an adjoint pair down here. All right. And so,
Hi, but sorry, before going on, do you want to maybe answer the questions? There was a question in the chats.
I'm sorry.
Basically saying there should also be the Frobenius relation, and if that's...
Yes, I'm sorry. You're absolutely right that I forgot the Frobenius reciprocity relation. That there really should be 8 axioms. My bad.
Okay, thanks.
Yeah, thank you.
Thank you.
Yeah, it would be cool if that one followed for free, but I don't think it does. Okay. Yeah, sorry about that. So I have these two adjoint pairs, and I could compose these together and get one big adjoint pair, right? So I could go from here to here, and I could go from here to here, and I'll have this big adjunction, which is the composition of 2 adjunctions. The guy on the left going from CP Tambara functors down to commutative rings, I'm going to call that restriction, which I'm going to write with it. I'm going to call it restriction, which is the same as the name of one of the structure maps inside a Tambara functor, which is quite confusing. So let me just call it R. It's capital R. CP down to E. Okay. And then on the right, I have this construction that I'm going to call C. Like this. Okay, and so this says I'm doing my R operation to go from CP Tambara functors to really E Tambara functors over the trivial group, which is just the same as commutative rings. And over here, I'm doing C from E to CP. I'm taking an E Tambara functor, i.e. a commutative ring, and I'm producing a CP Tambara functor. And this guy's called co-induction. Okay. And I did this whole story for CP Tambara functors, but actually the whole thing works exactly the same for any finite group G. We have exactly this picture, no matter what the finite group G is. It's exactly the same as what I just said. We have this underline construction produced by taking a G ring and looking at the various fixed points for various subgroups. And I can have this forgetful functor where I look at the bottom level, which comes with a G action, and I can forget that G action. And if I had just a commutative ring, I could boost it up to a G commutative ring by looking at all the functions from G to R, and so on. And this all fits together. It's exactly the same pair of adjoint pairs situation. Okay, cool. So we're going to use those. I think that concludes part 1. Yes. Now we're in part 2, which is really the first part of the title, which is what does it mean to be algebraically closed? Okay. So Right. Maybe I should just give some motivation before we jump into this part of the talk. So I said that CP Tambara functors or G Tambara functors more generally are some kind of generalization of commutative rings, and they're completely abstract algebraic objects. They're described by a bunch of sets and a bunch of operations and a bunch of morphisms, and all the operations satisfy axioms, and the morphisms compose with each other in specified ways, a completely abstract algebraic situation. And the category of CP Tambara functors, or the category of G Tambara functors more generally, is a category of algebraic varieties in the sense of universal algebra. There, you can talk about the free Tambara functor on a single generator, and so on. All the sorts of constructions you would like to say about commutative rings exist in exactly the same way for Tambara functors. There's such thing as ideals, and there's such thing as quotients, and you have free things, and etc., products and coproducts and all that. And so because of this, we might think that like classic ideas from commutative algebra and algebraic geometry should translate in a pretty straightforward way into the theory of Tambara functors. We have some kind of, we have lots of knowledge of commutative algebra. Maybe we like to think about localizations or varieties or the spectrum of a ring or whatever. And all those things hopefully should make sense for Tambara functors. And a lot of the time, the translation from ordinary commutative algebra to commutative algebra of Tambara functors is very straightforward. But a lot of the time it's not. And the definition of an algebraically closed field is something that is pretty subtle to translate over. And it's something we might care about if we want to do commutative algebra of Tambara functors. In general, if you want to do commutative algebra, you care a lot about the geometric points of rings, which are the maps to algebraically closed fields. And so it would be nice to know what are the algebraically closed fields in the category of Tambara functors. What do those mean? And so ordinarily, the definition of an algebraically closed field is that, okay, I have a field, so 0 is not equal to 1, and every non-zero element is invertible, and every non-constant polynomial in one variable has at least one root. Okay, an algebraically closed field is just defined in that sort of way. And most of that seems pretty reasonable for Tambara functors. But the definition of field gives you something not super desirable. And the definition of algebraically closed becomes quite tricky because it's really hard to say in the Tambara case, what does it mean to have a polynomial with coefficients in a Tambara functor? And what does it mean for such a thing to have a root? There is such thing as a free Tambara functor on one variable. There is such thing as like a polynomial ring, quote unquote. But that polynomial ring is an entire Tambara functor. It has all these different levels. And it's hard to say exactly what it should mean for some element at one of those levels to be a non-constant polynomial. It turns out to be quite tricky to nail this down. So trying to define an algebraically closed field in exactly the way I said earlier in like the very classical definition of algebraically closed field, you run into a lot of trouble. And so part 2 of this talk is exposition of some really nice ideas from work of Burklund-Schlank-Yuan to give ourselves a nice purely categorical definition of algebraically closed field that does apply very nicely to the category of Tambara functors. So, okay, so let's get into that. So I guess the perspective we're going to have on algebraically closed fields is that there are these central players in algebraic geometry. The algebraically closed fields are where the theory of algebraic varieties works well. And so the whole picture of classical algebraic geometry is that I have some algebraically closed field F, and then there's this correspondence between algebraic varieties inside Fn. So that's subsets of Fn, which are equal to the 0 loci of some set of polynomials. And those correspond to ideals of a finitely generated polynomial ring for the same n. Okay. And how does this work? I take some ideal over here, maybe it's generated by some elements, F1 through Fm, and I map it over. I get this thing called V of F1 through Fm, and we define this to be, it's all the points, I guess, X in F to the n, such that when I evaluate each of these polynomials at that point, I get 0. It's the common vanishing set of those polynomials. And it also turns out it's the common vanishing set of every element of this ideal. Just turns out that this construction doesn't care whether or not you had the entire ideal or not. It's invariant under ideal closure. Okay. So we have this correspondence from like classical algebraic geometry. We take ideals and we produce varieties, and this variety is literally just a subset of f to the n. And the really nice, the whole key point is that there actually is a bijective correspondence between algebraic varieties, subsets of f to the n, with this property that they are equal to the zero loci of certain polynomials, and ideals inside the polynomial ring, maybe more precisely radical ideals, but close enough. There's this nice precise bijective correspondence. And this only really works over algebraically closed fields. If I tried to do this over the real numbers, I'd have, an ideal in R adjoint x. You'd have the ideal x squared plus 1 in R adjoint x. And what's the zero locus of this polynomial f squared plus 1? It's empty. There's nothing that squares to -1. And also the ideal that is the entire ring. Well, where does the polynomial 1 vanish? Also nowhere. Okay, and so I have these two different radical ideals that both produce the empty set. The correspondence breaks when f is not an algebraically closed field. So it is important here for classical algebraic geometry to work really well that f be algebraically closed. And it turns out we can leverage this fact to eventually define what it means to be an algebraically closed field. It's going to turn out to be the case that algebraically closed fields are precisely the kinds of base rings over which classical algebraic geometry works. Okay, so let's talk about that. So part of this correspondence is in particular that I have the ideal on the left that is the entire ring, and the zero locus of that ideal is the empty set. There's nowhere that the constant polynomial 1 vanishes. And so okay, also that ideal is radical. And so this should be the only ideal in the left-hand side that has empty zero locus. There should be a unique ideal inside my polynomial ring that maps to the empty set over here, and it should be the entire ring. And that's the content of Hilbert's Nullstellensatz. So here's Hilbert's Nullstellensatz from I think it's from the 1800s, late 1800s. If you have an algebraically closed field, then at least this piece of the correspondence works. Whenever you have an ideal, it produces the empty set. Its zero locus is empty, if and only if it is the entire polynomial ring. If this ideal contains 1, then it is the entire polynomial ring. And this zero locus being empty says that there's nowhere where f1 through fm all simultaneously vanish. Okay. So one direction of this is easy. If I do contain the number 1 in my ideal, then my vanishing set will have to be where the polynomial 1 vanishes, and maybe where all other things vanish, and 1 never vanishes. So this direction is easy. And so let's forget about that direction. We're just going to say if. Okay, this is the statement that actually takes work proving. If this vanishing set is empty, then I actually started with the entire ring. And there's lots of interesting proofs of the Nullstellensatz. We're not going to do that today. But what I want to do now is rewrite the Nullstellensatz 14 different times into a new form that will be more pleasant. Well, okay, I guess that's a matter of preference. Into a new form. Okay, so let's first just take the contrapositive of this statement. That would just say, if 1 is not in this ideal, then the vanishing set is not empty. Great, easy peasy. Okay, what does it mean for the vanishing set to not be empty? It means that there is a point in n-dimensional space over the field f where all of the polynomials simultaneously vanish. That is a simultaneous root of all the polynomials. Okay, so here's version 2 of the Nullstellensatz, it's basically saying exactly the same thing. We're going to have an algebraically closed field f. We're going to take a bunch of polynomials in the polynomial ring. If the quotient ring here is not the zero ring, in other words, if I didn't quotient out by everything, in other words, if this guy didn't contain 1, then there's going to exist an F algebra homomorphism from that quotient ring back to F. And what does that F algebra homomorphism have to do? Such a homomorphism has to send each xi to some element of f, and it has to respect these relations, which says precisely, I've got a bunch of elements of f, and when I plug those numbers into my polynomials, I get 0. So by having a homomorphism like this, I get a point in n-dimensional space over f. I get n coordinates in f, and when I plug that point into my polynomials, they all turn into 0. And so this says exactly that actually there is a point in the 0 locus, that this set is not empty. Okay, cool. And this is written in like really direct language. I'm thinking about a finite set of polynomials, and I'm quotienting out by this ideal. And it turns out every ideal of the polynomial ring is finitely generated. The polynomial ring is Noetherian. So this really is the right statement of the Nullstellensatz, but it's kind of cumbersome to write these guys. And so let's just rephrase it a little bit. Okay, instead of writing this guy, I'm just going to say, think about some finitely presented F algebra. And a finitely presented F algebra just means any F algebra that looks like this. Great, up to isomorphism. So I'm going to have F be an algebraically closed field. I'm going to take a finitely presented F algebra. And here's the claim. If that finitely presented F algebra is not the 0 algebra, then there exists an algebra homomorphism back to F. What does it mean to be an algebra homomorphism? It means this composition is the identity. Okay, and that's exactly the same thing that happened here. I had an F algebra homomorphism from my finitely presented algebra back to F. Really exactly the same statement, but now just up to isomorphism. Okay, great. So that's the Nullstellensatz. And this is a true fact. This is a theorem of Hilbert. So we can think of this as an implication. This sort of says if F is an algebraically closed field, then finitely presented F algebras have the following property. And the following property is this guy. If my finitely presented F algebra is not 0, then there exists an F algebra map down to F. Okay. And the interesting thing is that this implication here, if F is an algebraically closed field, then this happens, is reversible. This actually turns out to be a biconditional. And so this was, I'm not actually sure who this is due to originally, but it's exposited really nicely in the work of Burklund-Schlank-Yuan. If I have any commutative ring R, then here are two equivalent conditions. Condition 1, R is an algebraically closed field. And condition 2, the conclusion of the Nullstellensatz holds. So we know this implication, that's the Nullstellensatz. This says if R is an algebraically closed field, then, okay, first of all, R is not the 0 ring. That's part of what it means to be a field. And also, if I have a finitely presented R algebra, which is not 0, then there is an R algebra map back to the ring R. And the other implication is actually pretty easy. So let me just quickly spell out how that goes. If you have, let's say I have a commutative ring that satisfies this condition, then first of all, it's not the 0 ring. Good news, I'm on my way to being a field. Secondly, let's show that it has no nilpotence. Actually, more generally, let's just take any element x in R, which is not 0. And then I'm going to think about the R algebra like this. Okay, that's a finitely presented R algebra. It has 0 generators and 1 relation. And if this guy is not 0, then it would admit a map back to R such that this is the identity. But that would be impossible because I killed my element x and then I mapped back in here and x was not 0. So that can't happen, but I'm assuming that I do have the conclusion of the Nullstellensatz. And so it must be the case that this guy was 0. And that says anytime I have a non-zero element, it generates the entire ring as an ideal. And so I'm a field, right? And so why am I algebraically closed? I take some polynomial, and then I just look at the R algebra, like so. And if F is not a constant polynomial, and I already know that R is a field, then this is not the 0 ring, and it is finitely presented. And so there will be a map back, and that exhibits a root. of the polynomial, right? So it's a pretty easy two-step proof. And so this is a complete characterization of what does it mean to be an algebraically closed field. You're not the zero ring, and every non-zero finitely presented algebra has a map back down to the base ring. Okay, great. So the nice thing is that this is a much more categorical kind of statement. I can write down everything that's happening here in the language of category theory instead of talking about elements and polynomials and stuff. R not being zero says that R is not terminal in the category of commutative rings. And R algebra is just a map from R to some other guy A. And finitely presented will take a little bit of work. We'll talk about that. Non-zero algebra, again, means that A is not going to be terminal in the category of R algebras. And R algebra maps are just, an R algebra map back to R is just a commutative triangle like this. So except for the finitely presented word, this is really easy to translate into raw category theoretic language. And then we could easily just port the definition over to the category of Tambara functors. All right. And so here's the definition that is due to Burklund-Schlank-Yuan. They define the notion of a Nullstellensatzian object, which is exactly doing this thing. You take this characterization of algebraically closed fields, and you say, what does it mean in general for objects in a category? So take any category with a terminal object, and I care that we have a terminal object because I need to make sure my algebraically closed fields are not terminal. And we say that a Nullstellensatzian object in that category is anything which is not the terminal object. And every algebra that's a map from my guy, which is not terminal, has a map back. Okay. Hopefully that feels all right. And the finitely presented word corresponds to this compact word. I won't say too much about what this means. Maybe very quickly, I can say that I think about this morphism x to y as an object in the slice category x over c, and I want this object to be compact in that category, meaning in x over c from xy to blank should preserve filtered colimits. Okay, that's what compact means. So it's a purely category theoretic condition, and it turns out in the category of commutative rings, this says exactly that you're a finitely presented algebra. These are completely equivalent conditions. And that's a more general fact about algebraic theories. Anytime you have a variety of algebraic objects in the sense of universal algebra, compact morphisms correspond exactly to finitely presented extensions. And so that's what's going on here. And the same thing happens for Tambara functors. So, right, so now we're in part 3 of the talk. What are the algebraically closed Tambara functors? And so I'll give a definition. An algebraically closed Tambara functor is a Nullstellensatzian object in the category of G Tambara functors. It's exactly this definition, which works just fine. I have a category. There is a terminal object in the category of G Tambara functors. So I can write down this exact thing. Compact makes sense always. Okay, so that's what an algebraically closed G Tambara functor is. That's our definition of algebraically closed G Tambara functor. It's a Nullstellensatzian object in the category of G Tambara functors. And just like for commutative rings, the compact morphisms, the compact algebras, are precisely finitely presented algebras, finitely presented in the right universal property sense. You can talk about free Tambara functors on some generators, and you can mod out by a finitely generated ideal, and those are the finitely presented Tambara functors. Okay, cool. So now the question is, what are these guys? So we're happy about this definition. What are they? Okay. And so here's maybe a first thought you could have. We had this adjunction before between G Tambara functors and G rings, where I can do this underline construction to take a commutative ring with G action and get a G Tambara functor. And I could take a G Tambara functor and look at the underlying level, look at the bottom level to get a G commutative ring. And so maybe we could say to ourselves, maybe I take the complex numbers with the trivial action, and I do that, and I do underline of that. And that Tambara functor looks like, at every level, it's just C, and all the restriction maps are identities, and all the transfer maps are multiplied by the index of some subgroup inclusion, and all the norm maps are raised to a power of the index of some subgroup inclusion. It's a pretty straightforward little Tambara functor, and each level of your Tambara functor is an algebraically closed field. And our morphisms of Tambara functors consist level-wise of ring morphisms. So you might think that this definition of Nullstellensatzian objects, which just has to do with morphisms in the category of Tambara functors, would tell us that when you have, level-wise an algebraically closed field, then you'll get a Nullstellensatzian object. And the answer is no, this is not true, which is kind of a bummer. And so I'll try to explain why. So basically the reason is that in the category of G-Tambara functors, you can have all sorts of different G actions. And here C only has the trivial action, which is quite restrictive. And that causes a problem in the following way. Okay, so we're going to think about the following finitely presented C algebra. So I start with C, and I adjoin one generator for each element of my group G. And I also adjoin inverses for all of those generators. And then also I mod out by the sum of the generators. If I add all those generators together, I get 0. And it's important here that G is not the trivial group. If G is the trivial group, that collapses the entire guy, and I get the 0 algebra. But if G is not the trivial group, then this algebra is not 0. And it is compact. It's a finitely presented algebra because I have finitely many generators and finitely many relations. Okay. Right, and non-zero because G is not the trivial group. Okay, so that's a morphism of commutative rings. And this guy comes with a G action. G acts by permuting the generators here. And this guy comes with a G action. G acts trivially. Okay, and this morphism is actually a morphism of G commutative rings. It is true that G acts trivially on the complex numbers inside here. Great. So I can do this underline construction to this morphism, and I get a morphism in the category of Tambara functors. In other words, I get an algebra over C-driv underline. And we prove that when you start with a finitely presented algebra and you do the underline construction, you get a finitely presented algebra. That's a key part of the proof. Takes a little bit of work. And so that's one thing we show. And still non-zero because the underlying construction reflects terminal objects, it turns out. Very, very easy to show. Okay, and if this guy was Nullstellensatzian, then this would admit a map back to the base. But it doesn't, for the following reason. What would happen if I had a map back to the base? Here's C-triv. The levels of C-triv look like just C. I guess I'm drawing the CP case or whatever, or just the top level and the bottom level. At the very top level of this Tambara functor over here, I have the G fixed points of that ring, whatever that is. And right, and at the bottom level here, I have the entire ring. And I can think about what would happen if I took X sub E, and first I transfer up. Well, transferring up does the Galois theoretic trace, and that adds together all the conjugates of X sub E, which is 0. And when I go back down, I get 0. And so, okay, so X sub E goes somewhere, it goes to some Y. And when I go up, that transfer goes to order of G times Y. And when I go back down, I get order of G times Y. But that means 0 maps to order of G times Y, and 0 has to map to 0. So order of G times Y has to be 0, and order of G is invertible in C. And so Y is 0. So this element had to go to 0. And that contradicts the fact that this element was actually a unit. Okay, great. So there's no possible map back. And so this guy is not Nullstellensatzian. Cool. All right, so that didn't work. It's not the case that being level-wise algebraically closed makes you a Nullstellensatzian object. And the problem was this, it was exactly this thing about C-triv having trivial action. C-triv, having the trivial G action here made it so that when I map up and back down, I just get some like multiple of the guy I started with. Nothing twisty can ever happen. I can never get some weird twist where XE transfers up to 0. That was sort of the abstraction here. And so to remedy that, we're going to look at this bigger adjunction. Here's our main theorem. So this is the little picture of the big picture we had before. We have these two adjunctions between Tambara functors and G commutative rings and commutative rings. And the thing we show is that the Nullstellensatzian Tambara functors are precisely the co-inductions of algebraically closed fields. And so what does that look like? That looks like I take some algebraically closed field F, and I look at all the maps from G to F, this big product ring with G acting by permutation of coordinates, and then I do this underline construction. And that's what an algebraically closed field has to look like. Or that's what a Nullstellensatzian Tambara functor has to look like. Great. And because we have this characterization, we know exactly which algebraically closed field it should be. The very top level of this guy is just F that we started with. And the very bottom level is a product of copies of F where F permutes the coordinates. And so this also lets us classify what are algebraic closures of fields. So if I have a Tambara functor, which is a field, meaning that morphisms to things that are not the zero ring are always negative. Or in other words, I have no exactly one proper ideal and it is the zero ideal. That's one way to say that. Okay, I have a field in the category of Tambara functors. Then I could talk about its algebraic closure. It turns out the fixed points at the bottom level will be a field in the usual sense. And then the algebraic closure of that field is an algebraically closed field. And I can take the co-induction of that algebraically closed field to get an algebraically closed guy, and K maps to this guy, and this is the algebraic closure of K. This is the smallest possible algebraically closed field receiving a map from K. Cool. And part 3, which turns out to be related in ways that I didn't have time to talk about today, is that if I have any commutative ring R, then the category of R modules is equivalent as a symmetric monoidal category to the category of modules over the co-induced Tambara functor. So this Tambara functor, there is such a thing as a module over a Tambara functor, and there's a category of modules over the Tambara functor, which has a symmetric monoidal product that's like analogous to the tensor product. And the category of R modules is a thing with a tensor product, and these are equivalent as symmetric monoidal categories. And so as a corollary of this guy, we get that the K-theory of R is the same as the K-theory of the co-induction of R. The K-theory spectra, these are just ordinary spectra, no equivariance. But I just do an ordinary K-theory construction to go from the category of modules to K-theory. There is such a thing as projective module and so on over a Tambara functor. And to my knowledge, this is sort of the only example known of a computation of the K-theory spectrum of a Tambara functor. So we get this for any commutative ring R, but in particular for algebraically closed fields, we see that the K-theory spectra of a Nullstellensatzian Tambara functor is the same as the K-theory spectrum of some ordinary algebraically closed field, which is pretty nice. And there's work due to Balmer, D'Ambrosio, and Sanders, which proves a similar result, but not for discrete algebraic objects, but in the category of G spectra. Okay. Great. I think that's about all my time. I guess I was going to say, here's like some random technical lemma we proved, blah, blah, blah. I guess the thing to say here is, in order to prove this result, we had to show in particular that the co-induction functor preserves Nullstellensatzian objects. And we proved something a little more general. We noticed that this co-induction functor is this right adjoint over here to this left adjoint R. And we write down a bunch of technical lemmas that let us deduce in certain cases, if I just have a generic adjunction between two categories, when does the right adjoint preserve Nullstellensatzian objects? And so here's one of those technical lemmas. This is the one that we actually use in this particular proof. But there are others that could be useful in other cases. We can also, for example, with this tool, classify all the Nullstellensatzian G commutative rings, or all the Nullstellensatzian G sets by knowing the Nullstellensatzian objects of sets, or other things like this. The tools should apply just as well. All right, I'll stop there. Thanks.